So let us continue our morning session with the next speaker, Andreas Klumper from the University of Wuppertal, who will tell us about conformal data of integrable Hamiltonians from nonlinear integral equations. Please.
Thank you very much, Chairman. And before I start my talk, I would like to thank the organizers, Filippo Colombo and Jan de Gier, who is no longer here, for the invitation and the organization of this very interesting workshop with a very interesting natural phenomena as a side product. I think there was another earthquake yesterday night, right? I missed out the walk, but I didn't miss out the earthquake. I mean, thanks for that. Okay, so this talk is about a pet subject of mine. So the conformal field theory predictions and calculation of conformal weights, etc., is just a motivation of this talk. We are all facing the problem of calculating eigenvalues of transfer matrices, Hamiltonians, and since many years I was interested in doing better than applying, let's say, linear integral equations for density functions that are defined for the roots. In a certain sense, you can also call or in my view, the final goal of today's talk is to deal with finite size data, often spin 1/2 Heisenberg chain with integrable boundary conditions that defy the application of the usual techniques, so to say, calculating finite size data and facing problems with beta ansatz structures, even when not having to deal with strings. So how to cope with such problems. Okay, anyway, I will start exposing the techniques. What we will be doing is we use commuting families of transfer matrices, many transfer matrices, not necessarily only the transfer matrix whose logarithmic derivative gives the physically interesting Hamiltonian, but also matrices that just commute with the physically interesting transfer matrix and allow for setting up interesting functional equations. And the eigenvalues of the Hamiltonian obtained from the physically interesting transfer matrix, and these eigenvalues are obtained from nonlinear integral equations that come by relations of the physically interesting transfer matrix and other technically appearing transfer matrices. I want to introduce the techniques pedagogically, and I want to introduce the T and Y systems by just starting with a 2D Ising model, which is the simplest. In a certain sense, it's a system without any problems. Then by looking at the hard hexagon model as an intermediate system, I will go to the generic two-dimensional RSOS models and spin 1/2 Heisenberg chain, and then introduce the, so to say, full so-called T system, Y system of transfer matrices, fused transfer matrices, and related Y operators. Actually, nonlinear integral equations based on the standard TQ relations will be more successful in view of applications to the spin 1/2 Heisenberg chain with non-parallel boundary fields. Why it is so, it will become clear only during the talk, in the course of the talk. So here I'm interested in this talk mostly in finite size calculations for zero temperature, but equally well one can deal with finite temperature calculations for the infinite system size. And this work, the work on the final topic, is a collaboration with Holger Frahm, Dennis Wagner, and Xin Zhang, who was Alexander von Humboldt Fellow with us. Okay, this is already, this is too far. No. Okay, why are finite size data interesting? I think all of us know the scaling predictions of CFT for the central charge and conformal weights. So a lattice system that realizes particular conformal field theory has low-lying energies of the following types. The ground state energy comes with a non-universal bulk term, but then there is a 1/L term with, so this is for periodic boundary conditions. The central charge appears as a coefficient in pi times velocity of the elementary excitation divided by 6 times system size. So when calculating the ground state energy and then plotting things or fitting things in this way, we get the central charge. From the excited states, which come with gaps or in units of velocity divided by L, we get the conformal dimensions, and also from, conformal dimensions and the appear sum of delta and delta bar in the energy, and the difference appears in the momentum. As I said already, the spectral data for the integral quantum spins we get by use of transfer matrices. Integrability allows us to define, let's say Young-Baxter, allows us to define a transfer matrix as a function of so-called spectral parameter, and then for arbitrary spectral parameters, for us, these will be arbitrary complex parameters. These transfer matrices commute, so they share a set of eigenstates that are independent of U, and the Hamiltonian, which is defined as a logarithmic derivative of the transfer matrix. In this form, we often get sums of local objects. This Hamiltonian shares the same eigenstates. All of that is standard, and from now on, let us focus on these transfer matrices and come back to Hamiltonians only at the very end of certain calculations. By the way, the thermodynamics for integrable systems can be obtained by combinatorial means. Yang and Yang developed a method. One has to minimize free energy functional, but there's also an algebraic way by tautorization of the Hamiltonian and mapping it back to a classical system with staggering, and then a suitable column-to-column transfer matrix, also in the literature it's called quantum transfer matrix, then allows to calculate the thermodynamical potential by just calculating the largest eigenvalue of that object, not being forced to calculate and classify all of the excited states. That's just a note. So how do we solve the 2D Ising model? I want to take a very simple approach. We take a certain parametrization, or let's say a certain representation of the 2D Ising model in zero external field, takes a transfer matrix, and then, well, the transfer matrix, as we know, is of free Fermion type, but if you don't know it, but you use these parametrizations that are suggested by the Young-Baxter equation, then we find that the transfer matrix evaluated at 2 different points, shifted by plus and minus I. So here I rescaled the spectral parameter suitably, that these 2 transfer matrices, complicated objects, but when they are evaluated at these points for arbitrary V, multiplied gives something simple, the identity operator or identity matrix times a known function. So T itself is complicated, but this product is simple. Now, to make the story short, for the largest eigenvalue, this functional equation holds for all eigenvalues, and for the largest eigenvalue, we have the properties that in the so-called physical strip, we have analyticity and absence of zeros. And then, of course, we can solve this functional equation in a simple way. We take the logarithm, and then we introduce Fourier transform, and the functional equation turns into linear equation for the Fourier coefficients. And it decouples, and then we identify the Fourier coefficients, and then we do the transform back. And then we get the result for the logarithm of the largest eigenvalue as a convolution integral with the logarithm of this explicitly known function f on the right-hand side. Okay, so in the further course of the talk, I will call these integrals. By the way, this kernel is 1/4 times hyperbolic cosine of pi v over 2. So this kernel will be called S, and the convolution integral is, of course, S star log F. Okay, that's an integral expression of convolution type. And when being interested in excitations, one can do similar things, but then one gets additional terms. This is under control. What else can happen? So there's something called hard hexagon model. Here, the product or similar product of the transfer matrix evaluated at these points V plus minus I is not just a known function times the identity. Here I so to say normalized out this function. There comes something else, but this something else, still unknown, is identical to the transfer matrix. So then we get a functional equation on the left-hand side, and on the right-hand side we have two unknown, the same unknown object. Then we do the same technique as before. We take the logarithm Fourier transform, and then we get an integral equation. So on the left-hand side, we have log of t. So instead of t max, I just write t. And on the right-hand side, we have S, the kernel convoluted with log of 1 plus t. So t on the left and right are same, unknown, but they can be calculated from iterative treatment of this equation. Now, why do we have this, this additional term, the driving term? That comes by the fact that in this case, the transfer matrix T has 0 of order L at the origin, and when solving this functional equation or rewriting this functional equation in terms of integral equation, it just pops up. All right, so what is the general situation, at least for systems with SU2 symmetry? The well, in inverted commas, full story is so for SU2 and Q-deformed SU2 systems and RSOS models based on this, and maybe Q-deformed spin-1 Heisenberg chains. The full story is one needs, in the course of taking the product of T with itself, something new appears on the right-hand side. And then looking at that, what appears new, and then looking at the algebraic properties, then again, something new happens. So, and this, in a nutshell, is the following. We have a series of transfer matrices. All of them depend on the spectral parameter. In a certain sense, T sub j can be understood as a transfer matrix with spin j over 2 representation in the auxiliary space. All of them commute for, any indices and any spectral parameters uv lead to commutation. The so-called T system is the following. Many functional equations exist. I should have actually cited here Kulish and Reshetkin and possibly many others for the fusion procedure. The fusion equations or relations are usually bilinear linear equations. But in 1992, Paul Pierce and I found out that also purely bilinear relations exist. On the left-hand side, we have a product of the same type of transfer matrix for shifted spectral parameters. And on the right-hand side, we have the identity plus, now comes product of T's with different indices, but the same spectral parameter V. Maybe we did not write it in this way in those years, but the algebraic structure is like that. Now, what do we do with it? If we define the product on the right-hand side as something we call Y, actually in those years we called it little t, then these objects Y satisfy this set of functional equations. It's just a consequence of this green line, then you get the blue line. Y sub j times Y sub j for shifted arguments gives a product of 1 plus Y's with different indices. And this has been generalized to higher rank systems by Kuniba, Nakanishi, and Suzuki in '94. And for higher rank, well, pointing out the analogy to discrete Hirota equations and introducing Backlund flow, that was done by Krzyzewski, Lipan, Wiegmann, Zabrodin in a couple of papers starting in '97, if I remember correctly. So what do we do with all that? So here, I like to apply the same technology as before. let's start with the y1 times y1 equation. On the left-hand side, this product with shifted arguments. On the right-hand side, so since there's no y0, we have just 1 plus y2. We take logarithm and then Fourier transform, etc. Then we get this integral equation. On the left-hand side, log of y1, its argument v, and on the right-hand side, we get a convolution integral with log of 1 plus y2. Now, if we only knew y2, we could calculate y1. But there are many of these y's, and for the other y's, a similar, transformation of the functional equation into integral equation gives this result. Log of y sub j is a convolution of the kernel S with the logs of the other 1 plus y's with shifted indices. Now that gives a set of integral equations for the y's, and the integral equations can be solved by iterative treatment. So you can switch on your computer, and then the integral equations can be iterated, and then you will see convergence. That's what you cannot do with a functional equation. Functional equations are, the left-hand side and the right-hand side are either difficult, and in the form of integral equations, we have convergence of iterative procedures. Now comes the slightly disappointing fact. After having calculated all the y's, you only need y1 in case of, let's say, the physically interesting system, and you can forget about the, let's say, infinitely many other y's, and then you focus on this, do the same as before, log, and yeah, you rewrite this functional equation into an integral equation. There you know the y1, do the integral, and then you have the transfer matrix T1. And yeah, okay, so far so good. And calculating eigenvalues, for the moment it's a ground state eigenvalue, is as good or simple for L equal 10 to the 10 as it is for L equal 2. So these equations are good for any L, not just large or small. They hold for 2, 10, 10 to the 10, etc. Why are they good? The integral equation, the integral kernel has exponential asymptotics and behaves nicely in all respects. That can be done, but for the finite size data, you don't need to do the numerics. The so-called dialog trick is enough, and by this dialog trick, you can express for the 1 over L terms the necessary integral to do. This you will probably somewhat recognize as the integral that appeared before, except that the kernel is replaced by an exponential. So something has been going on. So we want to calculate this integral, and there's a trick to do it without solving the equations for the y1. So even for large system sizes, L, the 1 over L terms do not by any linearization or simplification. There's still integral equations to calculate, and they are non-trivial. But in that limit, when the kernel and the driving terms can be replaced by exponentials, and the exponential has a nice property that the derivative of itself is proportional to itself, then you can express this integral without knowing the function y1 in terms of sums or differences of Rogers dilogarithm functions, where the arguments here are just asymptotics of the function y, actually of all the y's. So, but only the asymptotics need to be evaluated and to be inserted. And then, due to identities for Rogers dilogarithms, this, at first sight, horribly looking expression simplifies to this. And so here, although I did not tell before, I introduced the parameter R for the RSOS models. So these functional equations are pretty universal, but for the so-called RSOS models, there is an upper limit of the index, and that's little r. For the isotropic spin 1/2 Heisenberg chain, R would be infinite. So here you see that the RSOS models with general integer R realize the minimal unitary conformal series. And yeah, so this is some success story of the entire procedure. Well, these techniques can be applied to side and bond percolation, as we have done. But what is important for the rest of the talk is, or at the end of the talk, I will use this dilogarithmic trick in the evaluation of the analog of the central charge in terms of Rogers dilogarithms, where as arguments only certain asymptotic values of the involved functions enter. Okay, what to do about excited states? Similar equations hold with additional driving terms. With regard to the dilogarithms, it's maybe interesting to note that we get similar expressions, but now with non-standard contours. And the towers, the conformal towers, originate from circling the singularities of the integrand, I mean 0 and 1. So one can understand these structures in terms of Rogers dilogarithm. Okay, maybe a remark on thermodynamics. This was finite size, temperature 0. But the equations look like TBA equations, known from the Yang and Yang thermodynamics and maybe the Takashi-Suzuki classification of allowed bound states. One can do thermodynamics by a completely algebraic approach, as I mentioned before, via Trotter and the quantum transfer matrix. There's a lot of literature on that. And there, the TBA equations appear by these identities arising from fusion of transfer matrices. And here I've shown the thermodynamics of the Hamiltonians for the RSS quantum spin chains with parameters r equal 5 and 6. So this, I think I never showed it before in talks. The data are old. Specific heat is shown here with a maximum, and then it tails off to 0. At infinity, at low temperatures, it's linear. And the other curves are the inverse correlation lengths of the leading the leading correlations, and correspond to conformal data delta 2,2 and delta 3,3, and they show, so the inverse correlation lenses also show linear behavior at low temperatures, and at infinite temperatures they go to infinity, of course. So this is just a comment in passing. Now I would like to turn to the spin 1/2 Heisenberg chain. First to that with periodic boundary conditions, and then to the spin 1/2 Heisenberg chain with arbitrary integrable boundary fields, and want to contrast these cases in the following way. For periodic boundaries, this approach by the T and the Y system is a success story. Here's the Hamiltonian. We know it too well. So okay, the only intellectual challenge at this point is that here I call the number of sides of the chain n instead of L. Yes. I'm sorry. Okay, so we have Yang-Baxter. There's an infinite number of conserved charges. We use just the first one, the Hamiltonian, as the first logarithmic derivative of the T. One can look at higher derivatives. All of them commute mutually, and these are just local objects. And the magnetization, or any magnetization, any direction, commutes with the Hamiltonian and all of the Q's. Here again are these integral equations for the functions y, and as I said, so one can solve that. Actually, an infinite number of such equations to be calculated numerically is, of course, a challenge. One needs truncations, but okay, this is under control, and in the end, from the function y1, one gets the energy. Here is the beast. The bulk interactions are the same, spin-spin. And then we have boundary fields. This is the most general case, in case of isotropic bulk interactions. Due to SU2 invariance on the first side, we can force the field to point into that direction without loss of generality. At the right end, so there's no periodic boundary condition. There is a right end and an interaction with a boundary field number n. Here, by the still remaining U1 symmetry, we can enforce the y component of the field to be 0. Only HNZ and HNX appear. And then, okay, so this is what we want to investigate. For arbitrary values of H1, Z, HN, Z, HNX. And well, in the literature, it has been found out that it's convenient to parameterize these three fields, components of the fields, as P, Q, and Xi. So P and Q are the inverses of the Z components, and the Xi is a ratio of the transversal part at the right end divided by the longitudinal part. Despite that, we still have Yang-Baxter equation. The reflection matrix equation is satisfied. We have an infinite number of conserved charges for any choice of P, Q, and Xi as before, but the magnetization does not commute anymore with H and Qn. Therefore, the normal beta ansatz is not possible, but still, I mean, the technique by fusion, etc., and T and Y system hold. But now, when taking the still nicely looking functional equations and turning them into integral equations, then you discover that due to the changed analytic properties of these functions, driving terms appear everywhere. So we have infinitely many functions with always non-trivial driving terms, and this is okay. I mean, Fram et al. They made some sense out of that, but in total, it's not so useful. What can we do in this situation? I mean, first of all, I want to get rid of the infinitely many auxiliary functions and the infinitely many integral equations. Let's chop it down to something finite. How to do that? We come back to the old TQ relation. Let me explain that first for periodic boundaries. We look at the TQ relation. So T1 is the first transfer matrix in the entire series, and here we only need the T1. Q is the Q function. Then we have this relation where now phi is a short term for the power of the argument, power L here. It's again L, okay, another intellectual challenge. When defining functions A and A bar as first term on the right-hand side divided by the second term or vice versa, then one discovers that these two functions satisfy integral equations that are similar to before, and so to say with TBA structure, but now there are only two such functions, and so on the left-hand side, log A bar, on the right-hand side, log of 1 plus A and log of 1 plus A bar. With certain kernel, the kernel is defined here in by a Fourier integral. The driving term is before, and so this is for the isotropic case. And the functions that have to satisfy these equations are really nice functions. So this is just a freehand sketch. The real part of log of 1 plus A, it's actually log of 1 plus A, which is physically interesting because that enters the integral for the energy. So this is rather smooth, and the imaginary part is small, and there are two asymptotic regions, an inner region where the functions, real and imaginary parts, are just 0, and outside where they approach the asymptotics. And the transition is at the point plus and minus log L. So nothing bad about anything. So that can be iterated on a computer, it converges, it's just nice. If you wanted to investigate the XXZ chain with anisotropy, only the kernel here would change, but also in a very nice way. So nothing to do with strings, etc. So can this be applied to the, here in the bottom line. So it's, you have to, maybe the microphone is in your way. So little a is phi of v times q of v minus 3i divided by phi of v minus 2i times, still in the denominator, q of v plus I. Okay, it's just so to say left-hand side divided by right-hand side of the beta ansatz equations. I mean, but this is not always so that such constructions give good integral equations. Now, this is a slide with which I should actually skip. But I want to point out that many people worked on this general integrable boundary condition. Nepomucci, Fram collaborators, Nicoli, Fadela, Kitanin, Meillet, and Terras, and the Chinese group. Well, I should be less discriminatory. Cao, Yang, Shi, Wang, and also others. Then with certain methods, more beta-ansatz-like methods were used by Béliard, Pimenta, Crempé, Avant, Grosjean, Pimenta, Slavnov again. Okay, some kind of modified beta-ansatz, then separation of variables, and fusion, as I mentioned already, and for special cases, and one can use standard TQ relations. I want to use work by Cao et al. They have two sets of TQ-like equations. One has been reproduced by separation of variables. I have to use a second version of the TQ relations, which come like this. This looks ugly. Let us just focus on the general structure. T is on the left-hand side. On the right-hand side, we have Q divided by Q expressions. So in principle, this is a TQ relation. You can multiply one of the Q to the left-hand side, then you have TQ equal to sum over Qs. But there is something which is not of Q divided by Q type on the right-hand side. This is some explicit function divided by Q. And therefore, these TQ relations are called inhomogeneous TQ relations. And here are two Q functions, Q1 and Q2, but with zeros that are closely related, as you see. I just want to say that can be derived. And when you apply the standard methods of integrability, then the bulk term in the energy and the boundary terms can be calculated, but the order 1 over n terms are unknown. So so this is the subject or object of interest that I have. What do we do with that? I think you can only be spectators. I cannot explain why certain things work. I tell you, we take this TQ-like equation. We reparameterize the argument. I mean, it's mostly we rotate everything in the complex plane by 90 degrees. Then we get a sum of 3 terms, still of the type, well, explicitly known function times a Q1 divided by Q2. The first term and the last term is of that type, and then there is the inhomogeneous term, known function divided by Q1, Q2. And now then, so this we would always do. That makes the beta roots or the zeros of the Qs to be aligned mostly along the real axis, but they are not exactly on the real axis, they deviate from it. So that's a challenge. I mean, how to take into account all of these contributions. They deviate only mildly, but there are very many of those, and that sums up. It happens that if you introduce these combinations of those functions, and that you can set up closed set of integral equations, nonlinear integral equations. On the left-hand side will be logs of these functions. On the right-hand side, logs of 1 plus a bar, 1 plus c. And you see these combinations have been chosen such that the factorization of 1 plus a, 1, etc., is also in terms of factors that appear on the left-hand side. This was just tried, and we followed our own work on the TJ model, the supersymmetric TJ model, and we found out that these combinations are successful. Then we get these integral equations for the 3 functions a bar, and c on the left-hand side, on the right-hand side, to be inserted into a certain kernel, log of 1 plus a, etc. There's a driving term. The driving term looks terrible, yeah, okay. So there's log hyperbolic tangent, and then something else, combination of gamma functions, but these come without factors of n. the function c has a driving term which is a log of a polynomial. That's ugly. And what is also ugly is the kernel here is a 3 times 3 kernel. The 2 times 2 submatrix is the same that we know from the periodic boundary case. And then come additional terms. And the additional terms are Cauchy kernels. And they are ugly because they are long-ranged, and so they decay only very slowly, and they diverge at short distances. What to do with that? So before complaining too much, let me show to you the solutions for certain cases where it worked. The functions are again smooth, so they're not horrible. So the functions that I defined are shown here, real part, imaginary part of what we call log of 1 plus a. Now the difference to the periodic boundary case is that the imaginary function, I mean the imaginary part of the function does not show these little blips or something like that. It shows actually a transition, a winding by plus 2 pi I. And okay, the function log c also, actually it's log of 1 plus c. What is important, looks not so dangerous, it takes very small values. So the dangerous part actually is this winding in the imaginary part. That leads to problems. It leads to problems in the iterative treatment of the integral equations, because this kink means that the function a of x as a function of real argument x in the complex plane encircles the point -1. Well, the a of x encircles -1, such that 1 plus a encircles 0. And when doing that, the kernel applied to that function does no longer give small results, small values, but rather large values, because log of 1 plus a can take very large values. Yeah, so it's clear. And, okay, oops. The horizontal axis here is just the real axis, I mean, of the arguments x. So this is not in the complex plane. It's the real part and imaginary part of the function evaluated on the real axis. So here, this is real x. Yeah, and these are graphs. I also have plots of zeros and poles in the complex plane. That's something different. Okay, so the winding is a problem, but the functions themselves, they are nice. So how do we, yeah, okay, so there are several observations. So the nice case is, of course, psi is small. But for a finite value of psi, then the position of the kinks, the windings, I mean, when we have the transition, the position of these transitions, these positions are difficult to understand. When you look at that and you try to make some simplifications or do some elementary calculations, whatever we usually do, it does not work. I mean, there's no intuitive understanding for that. Yeah, in particular, as the driving terms take flat values, the driving terms go to 0, but still then somewhere, so to say, out of the blue, then comes this winding. So difficult to understand. For small psi, that's good. The kinks are far away from the origin. And actually, they go to infinity when you send psi to 0. In case, yeah, that's a parallel boundary field case. Okay, so what do we know? Yeah, in the case psi equal to 0, we can do simpler calculations. Then there are two cases to distinguish. Left and right boundary fields are just 0, and left and right boundary fields non-zero. So 1 and 2, and so 1 and 2. And then we get different finite size data. In one case, the 1 over n term is multiplied with 1, and the other case is -5. So it's a bit surprising, but then we checked our calculations with those of the literature, and we found agreement. So I hope I understand the paper by Sakawa and Suzuki correctly. So what is now, what is the problem of everything? So let me introduce again the terminology. We call this the position of this transition of the imaginary part from 0 to 2 pi kink. So that happens symmetrically for the ground state. And then there are 2 points plus minus x0 where the eigenvalue function takes 0 in the physical strip. The eigenvalue of function lambda is free of zeros except at the 2 points plus minus x0, and these are also zeros of the function little c. Yeah, so when we take our integral equation and some initial data and then we try to iterate, then usually everything diverges. And yeah, so it looks, if we increase n, that this parameter x0 and the kink move to larger values and get closer to each other. And in particular, when they get close to each other, then any hope is lost to do numerical calculations. Here, it's still friendly case with lattice size 1000. And I showed to you the results of iterations, numerical iterations for 100 iterations, and there are lines plotted after every 10 steps. Then you see when being off, I mean slightly to the left of what I showed you before, then by the iterative treatment, these lines move further to the left until they crash somehow. If we take these data, as I showed you before, I mean the proper solution, and we are slightly to the right, then it moves further to the right. Okay. Then we took a brave step. I mean, what I showed you until the last transparency, that was, so to say, our state of knowledge until a few months ago. And then we realized that in the thermodynamic limit, when n goes to infinity, the location of the kinks do not move to infinity. They stay finite. To make it short, they are in particular smaller than x0. And contrary to everything we can see from direct numerical calculations. So doing alternative calculations is rather difficult for large system sizes because you cannot deal with direct, I mean, these beta-ansatz equations. And doing the integral equation just by inserting a system size and then hitting the enter button leads to nothing. So we had to test analytically several possible assumptions, and what we ended up with, the only scenario which is free of contradictions is these kinks take a finite value. The parameter x0 scales with, I mean, grows like 2 over pi times log n. And then when putting everything into these equations, then taking a limit, a suitable limit, I mean, rescaling the argument and this x0 by log n gives us this. The kernels that appear also in the periodic boundary case, I mean, turn into, I mean, these integral expressions, I should say, turn into something algebraic. But the Cauchy kernel remains. So under rescaling, the Cauchy kernel stays invariant, and one gets these integral equations, simplified integral equations, but still integral equation. And now, when doing the iterative procedure here, then we get convergence, and these are the results. And what I want to point out here is the function little c diverges at x equal to 0. But the physically interesting function log of 1 plus a is a little bit like before, but it shows a jump at the point plus minus 1, which correspond to these log n points after the rescaling. And what we need to know for the finite size data are the limits on the left and on the right. Inserting that gives this. The ground state energy and then gives the bulk term and the known surface term. And the difference is a 1 over n term now with a dependence on the parameter xi. So here v is the velocity of the elementary excitations, and a parameter phi appears, and phi for finite but small values of xi is 2 times xi. And possibly for larger values of xi, we have this relation. But the message is, the finite size corrections are xi dependent, and this is the first result on this question. And we have to check this relation in the next weeks, but it's 99.9% sure that the 1 over n terms are dependent on the orientation of the boundary fields with respect to each other. Well, here are plots of zeros and poles of the functions 1 plus a and c. The only thing I want to point your attention to is this is for n equal 10 or 12. Then the extension of the distribution of zeros and poles in imaginary direction is larger than that in horizontal direction. But the limit we are interested in is n to infinity. And then this here extends to log n. And so this is very far away from this thermodynamic limit. I mean, in order to get something which looks like the thermodynamic limit, would need to enlarge the system such that here, this endpoint is 10 times farther out than it is now. But being 10 times farther out with a log n growth means that instead of n equal 12, we need to look at n equal 12 to the 10 for finding this by direct numerical calculations. Okay, so this is another plot of similar types. This is my summary. I presented 3 nonlinear integral equations for the Heisenberg Chambers broken conservation of magnetization. And we have found how to deal with it. We did calculations on a conjectured scaling limit. This works. And the finite size data we obtain, they actually depend on the orientation of the boundary fields with respect to each other. What we have to do is clear, I mentioned that, checking of this conjectured scaling limit. And why is this interesting? So we have many integrable systems where kernels, etc., and driving terms are difficult. There's, for instance, a 3-3 bar network model with SL/1 symmetry, where the kernel is at first sight even worse. It contains terms that do not decay, kernels that do not decay to 0, but increase linearly. And for the strongest, that is for the strongly staggered 6-vertex model. And for the 3-3 bar network model, I think the growth is logarithmically. So understanding how to deal with such situations is certainly worthwhile. And this is our first step. And I thank you very much for your attention.
Thank you very much for your talk. Does anybody have a question for Andreas?
You need the inhomogeneous term to solve this equation. You didn't try to solve them because I mean you can also obtain this TQ equation without an inhomogeneous term. I mean it would.
Yeah, but I think in whatever you do, you get TQ equations which contain a third term. Yeah, and maybe your question was maybe the inhomogeneity becomes homogeneous, but after all, I mean I know about 2 versions. Yeah. And originally, produced by the group of Kao et al. They use something like analytical beta ansatz or inversion identities of an inhomogeneous. So they were criticized for that, and then SOV came, separation of variables. But they presented formulas, etc., for the eigenstates, etc. But the beta ansatz equation are still the same, as far as I understand. And as I said, I need the second term. So the second version of these TQ equations, I mean, all of these expressions lead to the same. I mean, these functional equations that we know for the transfer matrix are satisfied and boundary condition. So they satisfy it, but one set of equations is more useful than the other. And so this is everything I can comment. So this works. If something else works, I don't know. Well, the fusion T and Y system approach does not work, although it looks so educated. So the T and Y system looks like the highest you can get and do, but not for this.
Just a comment also, people concentrate a lot of this antiferromagnetic case, but the ferromagnetic has some interest also.
Right. You are thinking of ASAP type applications. Yeah. Mm. Yeah. What traditional techniques could help? Yeah. So this here for coping with infinitely many beta roots that are almost lying on the real axis, but still deviate a little bit on how to sum up everything. Yeah. That would not happen for. Yeah. Okay. Understand. For magnetic case, it's still an ugly problem, right? Yeah.
The questions?
So if the CFT spectrum is under control, could you hope to get like CFT characters by like computing I don't know, like partition function and then trying to extract the asymptotics with this kind of techniques? Or?
You mean here for
yes,
the modified boundaries?
Yes, periodic or I don't know. Yes.
For the periodic case and for the more standard cases, that has been done. Yeah, okay. So it works. So for the spin 1/2 Heisenberg chain with of XXZ type, I did this exercise myself a long time ago. Well, I was not so much interested in really classifying everything, but I convinced myself that all of the eigenvalues are there. I did not evaluate the multiplicities. So what is the problem for evaluating the modular invariant partition function? You have to know or calculate the eigenvalues, but then you also have to do the combinatorics. How often a certain eigenvalue appears. That can still be a problem. Yeah. So then, well, what can you use? Maybe then, yeah, computer experiments. Maybe. I mean, the integral equations or dilogarithmic trick will not tell you about that. It only tells you that a certain energy is not only close to a particular value, it is the value. Yeah? So that's what it is good for. How often a certain dialog integral with a crazy path appears, that's a different question.
Any further question? Well, if not, let's thank Andreas again.